Today, we're going to tackle one of the wildest, most fundamental ideas in all of physics, quantum superposition. And to do it, we're going to tell a little story, a tale of two very different coins. Okay, so picture this. You flip a regular coin. While it's spinning in the air, you don't know if it's heads or tails, but you know for sure it is one or the other. That's our classical coin. Now, let's meet the quantum coin, or as we call it, a qubit. While it's in its quantum state, it's not just that we don't know the answer. It is literally both heads and tails at the exact same time. And that right there is the heart of it all. One situation is just a gap in what we know. The other is a deep truth about how the universe actually works. So the big question is, why does that one bizarre difference change absolutely everything? To get to the bottom of that, we first have to get really clear on what we mean when we say uncertainty in these two completely different worlds. See, the classical world, our everyday world, runs on what's called epistemic uncertainty. Now, that's a fancy term, but it just means we don't have enough information. The coin has a definite state, heads or tails. We just can't see it yet. If we were a supercomputer, we could calculate everything, the force, the spin, the air resistance, and predict the outcome perfectly every time. But the quantum world? It runs on something totally different, ontic uncertainty. This is a complete game changer. It means the uncertainty is a real, physical property of the qubit itself. It's not hiding its state from us. It genuinely does not have a single definite state until the very moment we look at it. Now, here's what's really cool. These two types of uncertainty are so different, they need completely different mathematical rules. Classically, we just use simple probabilities. But in the quantum world, we need something more powerful, something called probability amplitudes. These amplitudes are complex numbers, which just means they hold two pieces of info at once. And that second piece of info, called phase, has no classical equivalent at all. And as we're about to see, it's basically a quantum superpower. So, let's pull back the curtain and look at these secret rules that give our quantum coin all of its extra power. You can think of this phase as a hidden layer of information inside the qubit. Imagine that each possibility, heads and tails, is like a wave. Phase describes how those waves are lined up with each other. If they're in sync, they add up and make a certain outcome more likely. But if they're out of sync, they can actually cancel each other out. That effect is called interference, and it is the key ingredient for so many powerful quantum algorithms. So this is how we write it all down. A qubit state, that's the psi symbol, is some combination of state 0, which we can call tails, and state 1, which we can call heads. And those C values in front, those are our probability amplitudes. They tell us two crucial things, how likely each outcome is and what their relative phase is. For our regular old classical coin, the rule couldn't be simpler. The probability of getting tails plus the probability of getting heads has to equal 1. 100%. Makes total sense, right? Now, for the quantum coin, the rule looks just a little different, but that difference is everything. We take the magnitude of those amplitudes, we square them, and then they have to add up to 1. This little bit of math is how we translate from the strange, wavy world of complex amplitudes back into the real-world probabilities that we can actually measure. So how do we actually do a quantum flip? How do we push a qubit into that weird superposition state? Well, in quantum computing, we don't flip it with our thumb. We use something called a gate. The main tool for this job is called the Hadamard gate, or just the H-gate. You can think of it as the perfect, ultimate coin flip. If you start with a qubit that is definitely a 0, the Hadamard gate puts it into a perfect 50-50 blend of both 0 and 1. It's our go-to tool for creating these amazing quantum states. And this is a great way to visualize just how much more information is packed into a qubit. A classical coin state is just a single point, somewhere on a line between 0 and 1. But a qubit state, with its amplitude and its phase, needs a point on the surface of a whole three-dimensional sphere. We call it the Bloch sphere. It's just a much richer space of possibilities. All right, so we've built this beautiful quantum state, living in this world of infinite possibilities. But what happens when we actually decide to, look at it? This is the moment of truth. And hey, this isn't just some abstract idea. The famous Stern-Gerlach experiment proved it for real. They fired silver atoms through a magnetic field, and they expected to see a continuous smear on the detector screen on the other side. But that's not what they got. Instead, they got two distinct separate spots. It was the first hard proof that when you measure a quantum system, you force it to pick one, to collapse out of that fuzzy superposition into a single definite state. Now, here's the really crucial part. Measurement isn't passive. We actually get to choose how we measure. If we're using a programming framework like Qiskit, the standard measurement is along the z-axis of that Bloch sphere. That's like asking, is the coin up or down? But look at this table. By throwing in other gates right before we measure, we can basically rotate our question. We can ask about the x-axis, is it left or right, or even the y-axis, is it in or out, each time revealing a different slice of the qubit's hidden quantum information.
Okay, this is all incredibly cool physics, but what's the point? Why does it matter? Well, it matters because we can now write these strange rules into computer code. So let's see how we actually put superposition to work.
Using a tool like Qiskit, we can turn these mind-bending concepts into a straightforward workflow. First, you map your idea onto a quantum circuit with gates. Then you optimize it for the specific quantum computer you're using. You execute it on the real hardware, usually through the cloud, and then you analyze the results that come back, which are always probabilistic. Let's look at a real-world example, a quantum half-adder. This does basic binary addition, just like a circuit in your laptop. You can see it uses quantum gates like the C0 and the Toffoli gate to perform the same logic, XOR for the sum and for the carry. So far, this seems pretty familiar, but there is a killer quantum twist. And here it is, the big payoff. If we put our input qubits, A and B, into superposition with those Hadamard gates, they become both 0 and 1 at the same time, which means this one little circuit calculates the sum for 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1 all at once, in a single shot. That is the incredible power of quantum parallelism. So we started with a simple coin flip, and we ended up with an entirely new kind of computation. The rules of the quantum world are bizarre, they're counterintuitive, but they are undeniably real. And now that we have the tools to actually write those rules into code, the real question left is, what new realities are we about to compute into existence?